In a laboratory at MIT, physicist Rainer Weiss adjusts the mirrors of his interferometer one last time. The year is 1972, and he's chasing something that shouldn't exist, ripples in the fabric of space itself. His colleagues think he's wasting his time. Einstein himself doubted these gravitational waves would ever be detected, but Weiss knows something profound. The universe is not silent. It's screaming, whispering, singing the stories of its most violent births and deaths. He just needs to learn how to listen. 43 years later, on September 14, 2015, two black holes, each 30 times more massive than our sun, spiral into each other in a cosmic dance of destruction. The collision happens in a fraction of a second, releasing more energy than all the stars in the observable universe combined. The gravitational waves from this cataclysm travel for 1.3 billion years across the cosmos, weakening as they go, until they finally reach Earth and stretch LIGO's 4-kilometer arms by less than 1/10,000th the width of a proton. That day, humanity heard the universe's heartbeat for the first time. But what we discovered was troubling. The brightest, most energetic events in the cosmos, the very phenomena that should herald creation and renewal, are actually endings. Violent, spectacular endings. This is the paradox that haunts modern astronomy. Look up at the night sky, and you're witnessing a universe in the throes of its golden age, yet simultaneously in the early stages of an inexorable decline. The quasars that once blazed brighter than entire galaxies have gone quiet. The massive stars that forged the heavy elements necessary for life are burning out faster than they're being born. Even the universe's expansion, once thought to be slowing down, is accelerating, driven by a mysterious force that will eventually tear apart everything we know. We live in a cosmic moment that will never come again, a brief flickering candle flame between the darkness of the universe's youth and the cold emptiness of its distant future. And the brightest objects we can see are not celebrations of cosmic vitality, but funeral pyres burning in the night. To understand why the universe's most luminous phenomena are actually its death throes, we must journey back to when the cosmos was young and violent, a place where supermassive black holes grew fat on endless streams of gas and dust, powering beacons so bright they could be seen across the observable universe. Imagine the universe when it was only 1 billion years old, less than 7% of its current age. This was the era of the quasars, quasi-stellar radio sources that confused astronomers for decades because they appeared to be stars in our own galaxy but emitted radio waves like nothing ever seen before. When Martin Schmidt first measured the redshift of quasar 3C273 in 1963, he made a discovery that shook astronomy to its core. This star was actually 2.4 billion light-years away, making it one of the most distant objects ever observed. To be visible across such vast distances, it had to be shining with the power of 2 trillion suns. The young universe was a feeding frenzy. Galaxies were smaller, denser, more chaotic. Gas clouds collided and merged with reckless abandon, spiraling into the gravitational wells of newly formed supermassive black holes. As matter accelerated toward these cosmic monsters, it heated to millions of degrees, glowing brighter than entire galaxies before disappearing forever beyond the event horizon. The accretion disks around these black holes became the most efficient energy sources in the universe, converting matter to light with far greater efficiency than even nuclear fusion in stellar cores. But this golden age of quasars was also their swan song. Each photon that blazed across the cosmos represented matter that would never again contribute to the universe's luminosity. The black holes were consuming their own fuel source, growing larger and more massive, but also quieter as the nearby gas and dust was exhausted or blown away by the very radiation pressure they created. Dr. Priyamvada Natarajan sits in her office at Yale, surrounded by computer simulations showing the formation of the first supermassive black holes. Her models suggest these cosmic giants formed much earlier and grew much faster than previously thought possible. We're seeing quasars when the universe was only 700 million years old, she explains to her graduate students. These black holes contain billions of solar masses. The question isn't just how they got so big so fast, but why they stopped growing. The answer lies in a cosmic thermostat, As black holes feed and grow, their accretion disks become increasingly luminous. The radiation pressure from this light eventually becomes so intense that it blows away the surrounding gas, shutting off the black hole's food supply. This is the moment when quasars begin to fade, not because they're dying, but because they've become victims of their own success. Today, the quasar era is over. The Sloan Digital Sky Survey has cataloged over 500,000 quasars, but virtually all of them are distant and ancient, their light traveling billions of years to reach us. In the local universe, the cosmic neighborhood we inhabit today, true quasars are extinct. The supermassive black holes that once powered them still exist at the centers of most galaxies, including our own Milky Way, but they're starving, reduced to occasionally flaring when an unlucky star wanders too close. This pattern of brightness followed by darkness repeats throughout the cosmos on every scale. Consider the most massive stars, the blue supergiants and hypergiants that burn with the fury of 100,000 suns. These stellar behemoths live fast and die young, exhausting their nuclear fuel in just a few million years before exploding as supernovae or collapsing directly into black holes. The elements they forge in their cores, the oxygen we breathe, the carbon in our bodies, the iron in our blood, are scattered across space in their final moments, seeding future generations of stars and planets. But here's the cosmic irony. The very elements that make life possible are created by stellar death. Every atom heavier than hydrogen and helium was born in the nuclear furnace of a dying star. We are quite literally made of stardust, the cremated remains of ancient suns that burned out long before our solar system even existed. In the Chilean desert, the Atacama Large Millimeter Array points its 66 radio dishes toward a galaxy 13.4 billion light-years away. The radio waves they detect began their journey when the universe was only 400 million years old, during the cosmic dawn, when the first stars were igniting in the primordial darkness. But even these earliest stellar nurseries tell a story of impermanence. The galaxy they're observing is forming stars at a rate 1,000 times faster than the Milky Way today, a frantic burst of creation that cannot be sustained. Dr. Roberto Maialino, studying these ancient galaxies with ALMA and the James Webb Space Telescope, describes them as cosmic fireworks. They burn bright and fast, converting their gas reserves into stars so rapidly that they exhaust their raw materials within a few 100 million years. Today, these same galaxies are quiet, red, and dead, massive ellipticals populated by old, dim stars slowly fading toward oblivion. This is the great tragedy of cosmic evolution. The most spectacular phenomena are invariably the briefest. The gamma-ray bursts that can outshine entire galaxies last only seconds to minutes. The kilonova explosions that forge gold and platinum shine for weeks before fading. Even the cosmic microwave background, the afterglow of the Big Bang itself, grows fainter with each passing eon as the universe expands and cools. From the summit of Mauna Kea, astronomer Srinivas Kulkarni peers through the Keck telescope at a supernova exploding in a galaxy 100 million light-years away. The star that died was 8 times more massive than our Sun, and its explosion releases as much energy as our Sun will produce over its entire 10-billion-year lifetime. For a few weeks, this single dying star will outshine the 100 billion other stars in its host galaxy combined. But then it will fade, leaving behind only an expanding shell of hot gas and perhaps a neutron star or black hole, a dense, dark remnant that will persist long after the light has faded. Astronomy is fundamentally the study of light, Kulkarni tells his students. But what we're really studying is death. The light we see from stars, galaxies, and quasars is often generated in the final, violent moments of cosmic objects. The universe's brightness comes from its willingness to destroy itself. This destruction, however, follows a cosmic hierarchy. The most massive objects burn brightest and die first, while smaller, less massive objects can persist for trillions of years. Our Sun, a medium-sized star, will continue shining for another 5 billion years. But even it will eventually swell into a red giant, engulf the inner planets, and then shed its outer layers to become a white dwarf, a stellar corpse no larger than Earth but containing the mass of the Sun. Red dwarf stars, the smallest and most common stars in the universe, are the ultimate survivors. With masses less than half that of our sun, they burn their hydrogen fuel so slowly and efficiently that they can shine for hundreds of billions or even trillions of years. When the last quasar has faded and the last massive star has exploded, red dwarfs will still be burning, providing the only light in an otherwise darkening universe. But even these stellar centenarians cannot escape the ultimate fate that awaits all matter. In the far future, when the universe is 100 times older than it is today, the last red dwarf will exhaust its fuel and fade to darkness. The cosmos will enter what physicists call the degenerate era, dominated by white dwarfs, neutron stars, and black holes, the dark remnants of a once brilliant universe. The European Southern Observatory's very large telescope in Chile captures light from SN 1006, a supernova that exploded over 1,000 years ago. The expanding shock wave still glows in X-rays and radio waves, a cosmic fossil preserving the moment when a white dwarf star was pushed beyond its limits and exploded with the power of 5 billion suns. Medieval astronomers recorded this guest star as bright as Venus, visible even during daylight for several weeks. Today, we understand that SN 1006 was a Type Ia supernova, the explosion of a white dwarf that accumulated too much matter from a companion star. These explosions serve as standard candles for measuring cosmic distances because they all reach approximately the same peak brightness. It was observations of distant Type Ia supernovae in 1998 that led to the shocking discovery that the universe's expansion is accelerating, driven by the mysterious force we call dark energy. This acceleration means that the universe's fate is even more bleak than previously imagined. Instead of eventually contracting in a big crunch or expanding at a constant rate, the cosmos will stretch faster and faster, eventually entering what physicists call the Big Rip. Galaxies will be pulled apart, then solar systems, then planets, then atoms themselves as space expands faster than light can travel. Dr. Adam Rees, one of the Nobel Prize winners who discovered the accelerating universe, often reflects on the implications of his work. We've learned that we live in a universe dominated by dark energy, a force we don't understand that's driving everything apart, he says. It's humbling to realize that the ultimate fate of the universe is to become cold, dark, and empty, with matter spread so thin that no new stars can form. Yet even in this cosmic pessimism lies a profound beauty. The very acceleration that dooms the universe to darkness also means that the light from distant galaxies will eventually become so redshifted that it disappears entirely. Future civilizations, if they exist, will look up at the night sky and see only the stars in their local galaxy cluster, a cosmic horizon beyond which the universe appears empty and black. We are privileged to live in an era when the entire universe is still visible, when we can look back through time and witness the cosmic drama of creation and destruction playing out on the grandest scales. The Hubble Space Telescope's deep field images show us galaxies as they appeared billions of years ago, frozen in cosmic amber by the finite speed of light. We see spiral galaxies in their prime, elliptical galaxies in their dotage, and irregular galaxies caught in the violent act of merging. The James Webb Space Telescope, with its golden mirror unfurled in the cold darkness beyond Earth's orbit, is now looking even deeper into space and further back in time. Its infrared eyes can penetrate the cosmic dust that shrouds stellar nurseries and peer into the hearts of distant galaxies. But with each new observation, the same pattern emerges. The universe's most spectacular phenomena are transient, brilliant flashes in a cosmos trending inexorably toward darkness. In the Millennium Simulation, one of the most detailed computer models of cosmic evolution ever created, virtual dark matter particles dance through time, forming the scaffolding upon which galaxies are built. The simulation reveals how the universe's large-scale structure emerges from tiny quantum fluctuations in the early cosmos, growing over billions of years into the cosmic web of filaments, clusters, and voids we observe today. But the simulation also shows us the future. As dark energy continues to accelerate the universe's expansion, the cosmic web will stretch and thin. Galaxy clusters will become isolated islands in an expanding ocean of space. Eventually, even these clusters will dissolve as their member galaxies drift apart, leaving only individual galaxies, and eventually individual stars, alone in the darkness. Dr. Volker Springel, who helped create the Millennium simulation, describes the profound loneliness of the far future. In perhaps 100 billion years, an astronomer in the Milky Way, if there are any left, will look out at the universe and see only darkness beyond our local group of galaxies. They'll have no way of knowing that the universe was once filled with hundreds of billions of other galaxies. The evidence of cosmic history will have literally disappeared over the horizon. This cosmic loneliness is already beginning. The most distant galaxies we can observe today are racing away from us at nearly the speed of light. Their light stretched to infrared wavelengths by the expansion of space itself. In a few billion years, many of these galaxies will disappear from view entirely. Their light too redshifted to detect even with the most sensitive instruments. The Event Horizon Telescope, a planet-wide array of radio dishes, recently captured the first image of a black hole's event horizon, the point of no return beyond which nothing, not even light, can escape. The black hole in question, MADI 7 asterisk, contains 6.5 billion times the mass of our Sun, and likely began its existence as a quasar billions of years ago. Today, it sits quietly at the center of its galaxy, occasionally flaring when matter falls into its grasp, but mostly invisible except for its gravitational influence on nearby stars. This image represents both triumph and tragedy. Triumph because it confirms Einstein's general theory of relativity in the most extreme gravitational environment possible, and tragedy because it shows us the ultimate fate of matter in the universe. Black holes are the final destination for much of the universe's mass. They grow by consuming stars, gas, and even light itself, becoming ever more massive but also increasingly cold and dark. Stephen Hawking showed us that black holes are not entirely black. They emit a faint radiation due to quantum effects near the event horizon. But this Hawking radiation is extraordinarily weak, and for black holes with the mass of stars or galaxies, the temperature is colder than the cosmic microwave background. These black holes will actually grow larger as they absorb the background radiation, becoming colder and darker in the process. Only when the universe has expanded and cooled enough that the cosmic microwave background becomes colder than the black holes themselves will they begin to evaporate through Hawking radiation. For a black hole with the mass of our Sun, this evaporation process would take 1067 years, a number so large it defies comprehension, containing more zeros than there are atoms in the observable universe. In the radio-quiet depths of space, the Arecibo Observatory once listened for signals from extraterrestrial civilizations, scanning the skies for artificial patterns in the cosmic static. Though the Great Dish collapsed in 2020, its legacy lives on in the searches conducted by other facilities around the world. The lack of obvious alien signals, what Enrico Fermi called the Great Silence, might itself be connected to the universe's tendency toward darkness and decay. Perhaps advanced civilizations, if they exist, have learned to hide from the cosmic destruction around them. Maybe they've found ways to harvest energy from black holes or to survive the heat death of the universe. Or perhaps they, like the quasars and the most massive stars, burned bright and brief before fading into the darkness of space and time. Dr. Frank Drake, who conducted the first scientific search for extraterrestrial intelligence, often wondered whether we might be looking in the wrong places or at the wrong times. The universe is 13.8 billion years old, he would say, but complex life has only existed on Earth for a few 100 million years. We might be among the first technological civilizations in the universe, or we might be among the last. The possibility that we are alone, or nearly alone, in the vast cosmos adds another layer of poignancy to the universe's slow fade toward darkness. The consciousness that has evolved to contemplate the stars, to build telescopes and spacecraft, to peer back through time and glimpse the cosmic dawn, might itself be as rare and precious as the quasars and supernovae that light up the cosmic night. From the Planck Space Observatory, we have mapped the cosmic microwave background with exquisite precision, revealing the temperature fluctuations that represent the seeds of all cosmic structure. These tiny variations in the density of matter and energy, imprinted when the universe was only 380,000 years old, would eventually grow into galaxies, stars, planets, and perhaps life itself. But the cosmic microwave background also tells us about the universe's ultimate fate. Its temperature today is 2.7 Kelvin, just barely above absolute zero, and it continues to cool as space expands. In the far future, when the last stars have burned out and the last black holes have evaporated, this background radiation will be all that remains. A faint whisper of the Big Bang, growing fainter and colder until it, too, disappears into the quantum vacuum. The trajectory from the brilliant birth of the universe to its cold, dark end is not a story of failure, but of transformation. The hydrogen and helium forged in the first 3 minutes after the Big Bang became the raw materials for stars. The heavier elements created in stellar cores became the building blocks for planets and life. The energy released by dying stars illuminated the cosmos and may have triggered the formation of new stellar generations. Even black holes, those cosmic graveyards where light goes to die, play a crucial role in galactic evolution. The jets of high-energy particles they emit can trigger star formation in nearby gas clouds, while simultaneously preventing other regions from forming stars. They are both creators and destroyers, nurturing and culling stellar populations with equal measure. At the Laser Interferometer Gravitational Wave Observatory, scientists continue to detect the ripples in spacetime caused by colliding black holes and neutron stars. Each detection represents a cosmic catastrophe, the merger of objects so dense that a teaspoon of their material would weigh as much as Mount Everest. Yet these same catastrophes create and scatter the heaviest elements in the periodic table, seeding space with the gold, platinum, and rare earth elements that may be essential for technological civilizations. The universe's brightness has always been a byproduct of its violence. The gentle light of our sun is powered by nuclear fusion, the controlled merger of hydrogen nuclei under temperatures and pressures that would instantly vaporize any material object. The aurora that dances across Earth's polar skies is created when charged particles from the solar wind collide with our atmosphere at speeds of hundreds of kilometers per second. Even the warm glow of a stellar nursery is the result of gravitational collapse, matter falling inward under its own weight, heating up through compression until nuclear fires ignite. Dr. Sandra Faber, studying galaxy evolution at UC Santa Cruz, has tracked the cosmic star formation rate over billions of years. Her observations show that the universe reached peak star formation about 10 billion years ago, when the cosmos was barely 3.8 billion years old. Since then, the rate of stellar birth has been declining steadily as galaxies exhaust their gas supplies and dark energy pulls them apart. "We missed the party," Faber often tells her students. The universe's most productive era of star formation happened long before our solar system existed. We're living in the cosmic equivalent of the morning after, when the cleanup crew is sweeping up the empty bottles and turning off the lights. This decline in star formation means that the universe is already past its prime in terms of creating new light sources. Most of the stars that will ever exist have already been born. The massive blue giants that light up spiral arms and star-forming regions are particularly affected, as they require vast amounts of gas to form, and their powerful stellar winds blow away the very material needed to create their successors. The result is a cosmic population shift towards smaller, dimmer, longer-lived stars. The night sky of the far future will be dominated by red dwarfs, stars so faint that they would be invisible to the naked eye even if they were as close as our nearest stellar neighbor, Proxima Centauri. The brilliant blue-white beacons that make galaxies visible across billions of light years will be extinct, leaving only the cosmic equivalent of dying embers glowing weakly in the darkness. Yet perhaps this is not entirely a story of loss, but also one of persistence and adaptation. Red dwarf stars, while dim, are extraordinarily stable. They can maintain steady nuclear burning for hundreds of times longer than massive stars, providing consistent energy to any planets that might orbit them. If life exists around these stars, it would have vast amounts of time to evolve and develop. The recent discovery of potentially habitable planets around red dwarf stars like Proxima Centauri Trappist T-1, and to a 715, suggests that these dim suns might be the universe's best hope for hosting long-term biological and technological evolution. While massive stars provide the spectacular fireworks that make the universe bright and beautiful, red dwarfs offer something perhaps more precious: time. In this context, the fading of quasars and the exhaustion of massive stars might represent not the end of cosmic evolution, but a transition from a chaotic, violent youth to a more stable, sustainable middle age. The universe is trading spectacle for longevity, brightness for endurance. The civilizations that survive this transition might find themselves inheriting a cosmos that, while dimmer than before, offers billions of years of stability and gradual development. The Kepler Space Telescope, before its mission ended, discovered thousands of exoplanets orbiting other stars. Many of these worlds exist in systems billions of years older than our own, having formed when the universe was still in its star-forming prime. If life arose on these ancient worlds, it would have had billions of additional years to evolve beyond anything we can imagine. Perhaps some of these hypothetical civilizations learned to harness the energy of their dying stars, building Dyson spheres or other megastructures to capture every photon of fading stellar light. Maybe they developed technologies we can't even conceive of, finding ways to extract energy from black holes, dark matter, or the quantum vacuum itself. They might have transcended their biological origins, becoming forms of consciousness we couldn't recognize as life. Or perhaps they learned the deepest lesson of cosmic evolution. That brightness is temporary, but information can be eternal. The pattern of atoms that makes up your consciousness, the arrangement of neurons that stores your memories, the genetic code that carries the history of life on Earth. These are forms of information that persist even as the matter that carries them is constantly being recycled and replaced. In the quantum mechanical view of reality, information cannot be destroyed, only transformed. When a star dies and becomes a black hole, the information that described its mass, spin, and electric charge is preserved in the black hole's properties. When that black hole eventually evaporates through Hawking radiation, the information must somehow be encoded in the outgoing particles, though how this happens remains one of the deepest mysteries in physics. Dr. Juan Maldacena, working on the holographic principle and the information paradox, suggests that the boundary between existence and non-existence might be more fluid than we imagine. Information wants to be preserved, he says. Even when matter falls into a black hole or when particles decay into energy, the information they carried finds ways to persist. The universe might be fading in terms of light and heat, but it's becoming richer in terms of information and complexity. This perspective offers a different way of thinking about cosmic death and renewal. The hydrogen atoms forged in the Big Bang become helium in stellar cores, then carbon and oxygen in dying stars, then iron and nickel in supernovae, then exotic particles in neutron stars, and finally pure energy in black hole evaporation. At each stage, matter transforms, but information accumulates. The universe becomes more complex and interesting even as it becomes darker and colder. From this view, we are not witnessing the universe's death, but its transformation into something beyond our current understanding. The quasars that have gone quiet, the massive stars that have exploded, the gas clouds that have been exhausted. They have all contributed their information to the cosmic library, adding new chapters to the story of existence. The search for extraterrestrial intelligence continues this tradition of information gathering and preservation. By scanning the skies for artificial signals, building repositories of human knowledge, and sending messages to other star systems, we are participating in the universe's drive toward greater complexity and information content. Even if we never make contact with alien civilizations, the very act of searching and preserving knowledge adds to the cosmic information store. In the end, perhaps the brightest objects in the universe are dying not because death is an ending, but because death is a transformation, a way of passing information and energy to the next generation of cosmic evolution. The quasars fade so that galaxies can form. Massive stars explode so that planets can exist. Species go extinct so that new forms of life can emerge. Civilizations rise and fall so that consciousness can explore new possibilities. We live in a universe where brightness is borrowed, where every photon of light represents matter converted to energy that can never be recovered in its original form. But we also live in a universe where this temporary brightness has created something unprecedented. Observers who can look back through time, understand their cosmic heritage, and contemplate their place in the vast sweep of cosmic evolution. The light from the most distant quasar visible to our telescopes left its source when the universe was less than 1 billion years old. It has been traveling through space for over 13 billion years, passing through expanding voids, around massive galaxy clusters, and finally into the mirrors of our most sensitive instruments. In a very real sense, we are seeing the universe as it was in its infancy, preserved in light like insects in amber. But this light is also a gift from the past to the present, energy and information passed down through cosmic generations, carrying within it the story of when the universe was young and wild and brilliant beyond imagination. We who receive this ancient light are the universe's way of remembering its own history, of bearing witness to the cosmic drama of creation and destruction that has been playing out for nearly 14 billion years. As the universe continues to expand and cool, as the last quasars fade and the last massive stars explode, as dark energy pulls galaxies beyond the cosmic horizon, we may be among the final generation of observers to see the cosmos in its full glory. The night sky we look up at, filled with galaxies and star clusters, nebulae and stellar nurseries, represents a view of the universe that may never be seen again. In the far future, when the universe is cold and dark and empty, there may be no one left to remember that space was once filled with light. The story of quasars and supernovae, of stellar birth and galactic collision, of the brief moment when matter organized itself into patterns complex enough to contemplate their own existence, may be lost forever to the expanding darkness. Unless, of course, information really is eternal. Unless consciousness finds a way to persist beyond the death of stars and the evaporation of black holes. Unless the universe's transformation from brightness to darkness is not an ending, but a beginning, the opening chapter of a story we cannot yet imagine, written in forms of matter and energy that exist beyond our current understanding of physics and biology. Perhaps the brightest objects in the universe are dying not because the cosmos is ending, but because it is getting ready to become something else entirely. Something that doesn't need light to see, that doesn't need heat to think, that doesn't need matter to exist. Something that has learned to extract meaning from darkness and find beauty in the quantum vacuum itself. Until that transformation is complete, if it ever is, we remain witnesses to one of the most spectacular shows the universe has ever produced. The gradual fading of cosmic light, the slow dance of destruction and creation, the temporary triumph of complexity over entropy. We are stardust contemplating stars, cosmic dust that has organized itself into patterns capable of understanding their own cosmic origins. The brightest objects in the universe are dying because brightness cannot last forever. But in their dying, they light up the darkness long enough for something beautiful and impossible to emerge. Consciousness, understanding, and the recognition that even in a fading universe, there is still time for wonder, still time for discovery, still time to ask the questions that make existence meaningful. And perhaps, in the end, that is enough.